When you draw a Lewis structure, though, it's not that we can actually see the electrons, how the electrons are being distributed, and it's based on the observation in the laboratory and the measurement that we did there. Okay, so sometimes when you have certain type of evidence there, you can argue, well, this is the proof for this particular Lewis structure, and then other people may have other observations there, and based on that, and there's another argument. So up to the 1990s there, and you think Lewis structure has a fairly is a fairly developed theory there, but still people are making argument one way or the other about a particular structure, Lewis structure for a particular combination of atoms, there are molecules or ions for that matter. So for more practice that's available in the textbook there, now make sure you go through the, when you read the textbook there, make sure you look at the examples there and try to do the practice questions, practice problems following each of the examples there. Now, so far we've been talking about when we draw Lewis structures, we've been talking about things that follows the octet group. And again, for any rules that we have here, and there's always exception. The first exception is, well, there are certain atoms in the periodic table, they can take less than 8 electrons. So that's our first exception there. And one example would be boron trifluoride. Now, boron trifluoride is a compound that exists in nature. Okay. We can synthesize boron trifluoride. However, if you look at the Lewis structure there, fluorine brings being group 7A, so you have 7 valence electrons there, and boron group 3A. So 3 fluorine atoms and plus the 7 electrons each, and so that's 21 electrons there. 21 electrons plus 3 electrons here, so total 24 electrons there. And the thing here is that each one needs 8. Well, if you look at the structure there, boron does not have 8. Boron only has 6. So that's one of the exceptions there. And some of the elements can have less than 8 electrons. Now these kind of elements there, they do have the orbital available. When you get into the second period and third period there, you do have the orbital available. It's just not, we don't have enough electrons to fill in those rooms there. Like you have a large hotel, you have extra rooms there, but not enough gas. So in this case, if you have ammonia with nitrogen, lone pair of electron on nitrogen, well, these two will readily combine with one another, reacting with one another. Every time you have a combination of different molecules there, then you have a chemical reaction there. So what happens here is that nitrogen has a lone pair of electrons. Boron has a vacant room. So the two can react with one another and forming a chemical bond between nitrogen and boron. Now in this case, we call this particular bond a coordinate covalent bond, simply because the electrons that forms the nitrogen-boron bond come solely from nitrogen. Boron only provides accommodation or room, if you will, to accommodate those 2 electrons there. So this is one of the exceptions there. Okay, so that's fewer than atoms with fewer than 8 valence electrons there. Boron, aluminum, beryllium, these are the elements, very few elements there that will actually be the exception of the octet group. These are the situations where you have fewer than 8 valence electrons. Now, the result of that is these compounds, like boron trifluoride, boric acid, these compounds are very reactive. So whenever you have moisture, water, now remember the Lewis structure of water, H2O. You got 2 lone pair of electrons on oxygen. So moisture is present pretty much in the air and constantly. And so if you have a compound that is an exception of the octet group when you only have 6 valence electrons there, well, this molecule will attack those molecules with atoms and with less than 8 valence electrons. Therefore, those compounds are very reactive. If you expose them to the air, where moisture is available, they're going to react with one another. Aluminum trichloride, which is a catalyst used in many organic reactions there. And when we purchase aluminum chloride, you will see the compound came in with multiple types of packaging there. We just want to make sure there's absolutely no moisture in there, because if you add moisture, water to aluminum chloride, you generate hydrochloric acid in the hydrogen chloride gas. So it will not only destroy the aluminum chloride and making it unusable as a catalyst there, and will also emit harmful fumes. So, and that's something that you do want to pay attention to. Whenever there's an atom involved in a molecule with less than 8 valence electrons, they're very reactive. So this is the situation when we have fewer than 8 valence electrons. And as you can guess, there are exceptions that the elements with more than 8 valence electrons, once you have the all the electrons distributed. Now this is actually a double exception there, and we say xenon noble gas elements there, they normally do not participate in chemical reaction forming chemical compounds with others. Well, here xenon actually react with fluorine and oxygen and form this compound here. And if you count the total number of valence electrons on the central atom xenon here, well, you see there are 6 pairs. Well, total of 6 pairs of electrons. 6 pairs, that means 12 electrons. So this element can actually have more than 8. So one situation is fewer than 8, and the other situation is more than 8. Now, this will only happen on central atoms that are in the 3rd period or higher. Now, when you say 3rd period, that's n equals to 3. N equals to 3. When n equals to 3, you have 3s, 3p, and 3d. There are 5 orbitals on the 3d subshell. So not all those 5 orbitals are completely occupied. So you've got a fairly large hotel and plenty of empty rooms there. And this is where the situation, when you have empty rooms there, and the atoms, when you have more than 8 valence electrons, the central atom will be able to accommodate those extra valence electrons there. Okay. Now the surrounding atoms there, or the terminal atoms there, they're still having 8 valence electrons. But this exception only applies, and these both exceptions that we talked about only applies to the central atom. The central atom will either have fewer than 8 or more than 8, and those are the situations there. Okay, so these are the 2 exceptions there. Another time, another situation when you look at the exceptions there is that, well, when you talk about electron pairs, that means you have to have an even number of electrons. But what happens if you have a group 5A element combining with group 6A element? You end up with 16, you end up with 11 electrons there, or 17 electrons for that matter. So nitrogen monoxide, nitrogen dioxide, these are the examples there. Okay. Now when you have odd number of electrons there, you end up with what we call free radical. Now a free radical means there is a central atom there with a lone electron, a single electron there, not a lone pair. A lone pair would still be okay. And this is a situation, you have a single electron, not pair. Now in this case, they're very reactive, and they do not exist in large quantities or commonly in nature, so they're rare. And they're very reactive. Whenever you have free radicals, their free radicals will readily react with other things that has the extra valence electrons. And so they're going to combine, they're going to react. And this may be where the term radicals come from. When we call them free radicals in chemistry, they're very reactive, and sometimes they go to the extreme when the chemical reactions happen. So in the political arena these days, and you hear the people on the left side, on the right side, and those are the radicals. And they're nuts. Stay away from them. Okay, and now you know in chemistry we have a term to describe their behavior, and they're just going crazy